All right, folks, so I want to show you this ED202. Let me bring the web page in. All right. So here, ED202, the classic buffer overflow without shellcode. All right. And this has all the elements you need, and it's simpler, and I just tested it, so it's going to work, as opposed to the format string attack, which failed at the punchline. So this one here, by the way, I'm still using Python 2, so let me mention, if you're using Debian 11 like I am, what you have to do is sudo apt install Python. That will put Python 2 on your machine. And then you have Python. If you just run Python, you're in Python 2, so I can exit. So you have Python 2 if you want to use it. I'm hoping I'll get the Python 3 version of this stuff written by next week, but right now my instructions use Python 2. So be warned about that. And then let me shove these instructions to the side and go through ED202. So, you make this program, pwd.c. I give you the source code. All right, and this program has a main routine which runs if some test is true, then print fail, otherwise win. And the test PW prints out the address of the password as a pointer, a hexadecimal value, which is just so we can check to see if address space layout randomization is on. And then it asks the user for a password, but then no matter what password you give it, it returns 1. So every possible password is wrong. This will always be true, so it will always print fail. You'll never win, no matter what password you get in. And of course, the goal is to print out the you win message. You want to trick it into winning, even though the logic that the programmer put in says you will never win. All right. So that's the program. And the point, of course, is it used fgetS to read the password from standard in, and it lets you read in up to 50 characters, but it only reserved 10 characters for the password. So here we have a buffer overflow. We can inject some extra characters, and we should be able to use that to redirect to the win function. So that's what we're going to do. So you compile this thing, and then let me just go through all the steps here. And by the way, since I'm going to run 32-bit code on a 64-bit Debian 11 machine, all I would need is multi-lib, and I'm not even sure I need that. I was reading in an article today, they said Debian 10 and Debian 11 actually by default let you run 32-bit code on 64-bit OSs, which I didn't know. Now, there was a student that sent me a question in Canvas saying I can't run 32-bit code on my 64-bit machine, but they didn't tell me the OS, and I think it was Ubuntu. And I sent back a link to an article. I think you might have to do something not obvious to enable 32-bit code on 64-bit Ubuntu. So anyway, you'll probably have an easier life if you use Debian. But anyway, now to compile this thing, I did it this way. The -G means includes symbols, so you can see the source code. -M32 means 32-bit. Put the output in pwd32 and create pwd.c. So this creates pwd32, and there it is. I can enter a password of A, and it will then say fail. And notice the address is D5B6. Now if you run it again, it's still D5B6. If you run it again, it's still D5B6 because I have address space layout randomization turned off. Now just for completeness, let me turn it back on so you can see what it does. If I elevate to root and then echo 1 into this system variable, randomize VA space in the kernel, and then exit from root. And now I do that same test again where I run this program, A, run it again, A, and you see it's different every time. So that's what happens if address space layout randomization is on, which is the default condition of modern operating systems. And I want to turn it off for the exploit we're doing today. We don't want the addresses jumping all over the place. We're not writing a good enough exploit to handle that yet. All right, now it should be off again. Yep, now it's the same every time. The address is not moving. So we can debug the program. GDB -Q. Password tab completion does not work for some reason. All right, now I can list 1 to 13, and we can debug it using source code instead of assembly code if we like. And so here I'm going to enter the test PW function, and here is where the buffer overflow is going to take effect as I put in a password that might be too long. So I'm going to break at line 9. So I'll be able to see the condition of memory after the overflow. All right. So I run it. I put in 1, 2, 3, 4, 5, 6, 7, 8 A's. And then I go info registers. And here I see I am at EBP is 588. That's what I'm doing this for. I know where the bottom of the stack is. So now I can examine the stack. X, say 12X, ESP. And I'm looking for 588. So 588 is here. So that is the stack frame. And the next value is the return pointer. And the current return pointer is 56, 55, 62, 61. All right. So that's fine. And if I continue, it will print fail. That's the program operating normally. Now I'm going to overflow the stack. And I'm going to overflow it with 40 characters. There are 4 A's, B, C, D, E, F, G, H, I, J. The first 10 letters 4 times each. Now I examine the stack. Well, first I'll get the registers again, and I'll see that EBP is still 588. It did not make the stack any bigger, even though I put in a value too big, which is the fundamental problem with C. So let's see what the stack frame looks like, which is X12X, ESP, ending at 588, which is here. Okay. And as you can see, this value has been overridden by 46, 46, 47, 47. Now, this is 41, 2, 3, 4, 5, 6. So it was the last 2 F's and the first 2 G's that ended up in the stack pointer. So those 4 bytes control the next address. So we can now put any value we want in the instruction pointer. And the value we want to put there is, of course, win. So we disassemble win. And here's where the win function begins. So those are the 4 bytes we want to put in, 56, 55, 62, 17. So now we just have to create a Python exploit file that will create this string with those 4 bytes replaced by the address of the win function. So that was this address. I'll just copy it for now and then quit. And yes, and I know this is working because I set it up before we started. I've got an exploit file, and I'm just going to paste in that thing again so you can see it in a comment. There, that's the address we're trying to hit, 56. So I already pasted it in here. This was the one on Debian 10, and you can see my Debian 11 is a little different. So I'm using Debian 11, so I have to hit this value. So it's the prefix is everything up to the first 2 F's. Then you put in the EIP you want to hit, and then you put in the remaining stuff, because remember, I recommend always keeping your exploit the same length. And for these simple cases, it doesn't matter, but for some cases coming up later, it will matter, where a different exploit string would actually hit a different bug and drive you nuts. So this has to be that address backwards. the high byte first, 56, 55, so that's 56, 55, 62, 17. That's how you do it. And then prefix, EIP, and postfix. So if that works, that's exploit. So if I run that, it prints out this thing, A, B, C, D, E, D, F, F. Then here's the 4 bytes I changed. Looks like one of them was unprintable, and 3 of them are printable. And so that's making the string I need. So we can test it in the debugger. Oh, and what I'm going to do is I'm going to run this thing and put that string in a text file. This is one way to do it. It's not the only way to do it, but this is going to take that exploit and put it in an attack file, which contains my attack string. And if I do ls -l, the attack string is 41 bytes long, which is what I wanted. 40 bytes, and then there's a carriage return at the end. Why is it different in Debian 10 versus Debian 11? I don't really know. But everything does change when you change versions. So the amount, something about the compiler, something about the memory layout, something about the C library, lots of things are changing. I don't know exactly why, but it's very common that things change. This is probably the number one question I always get in all these projects. If people try to copy my demonstration code and run it, you have to be careful. You almost always have to adjust some addresses and stuff because it's different on every machine. So often you have to pay attention and make small changes to make these things run. Anyway, so there's my attack string. So I run this in a debugger. PWD 32. All right, and now I put in the break 9 again. And now I'm running with arguments and taking the data from that file. This is another way to do it. So it's going to run. Less than means input redirection. So it's going to take the input from that file that contains the 40-character password. Yeah, you're welcome. Instead of me typing it in, because some of the characters might be untypable. And that's the thing that's giving me sort of a little bit of trouble in Python 3. Python 2 makes it very easy to print unprintable characters, which is kind of an oxymoron, but it's what you have to do here. All right, so it's going to run, taking the input from that file, and now it hit the breakpoint, and now we can examine the stack. So info registers. EBP is still the same, D588. So if we examine the stack, 12x ESP, 588 is here. So it's going to go to 56, 55, 62, 17. That sounds pretty good. I'm just going to check by disassembling win again. That 56, 55, 62, 17, it looks good. So if I continue, it prints you win. So I have managed to exploit the program. By the way, this may seem like a weak attack. What I did was I just moved the pointer to a different piece of code that the developer put there. But this will actually turn out to be the most important kind of attack as we go ahead, because the original Aleph null type buffer overflow that was published in Frac magazine had you inject shellcode on the stack and run that code. And that was powerful and made a whole decade worth of malware. And around the time of Windows Vista, Microsoft put in some strong defenses to stop that. So you could not run code you injected anymore. So you ended up doing this. You ended up using code that was already there. That's return-oriented programming. So this more basic technique, where you don't inject any code, you just use the code in the different order than the developer intended, turns out to actually be the more powerful attack because it overcomes some defenses. Anyway, this is not as wimpy as it might seem. By the way, notice the program still crashed because we did not restore the EBP to a good value. So we were able to run the uwin function, but we were not able to return from the uwin function back to the operating system correctly. So we made a sloppy attack, a sloppy exploit, which accomplished the goal but then crashed. A more careful exploit would accomplish the goal and then exit normally. All right. So now you can also do it with a 64-bit code, and that's here explained. I don't think I'll demonstrate it live, but you can just recompile the thing without the M32 switch to make 64-bit code, and then you can do the same thing in 64 bits. And all that happens is the name of the registers changes from EBP to RSP and RBP. The registers get longer, of course. They're 64 bits long. Here's the R instruction pointer. And again, you can just do the same thing. You overflow the stack. Now it's going to be 8 bytes for the address. And so you're going to have to disassemble Win and get the 8-byte address of that. And then you're going to have to make a Python exploit with that 8 bytes. And notice, by the way, it's got null bytes in it. Now, it turns out to be okay because the null bytes you need to add is at the end. But what's really going on is anything after the first null byte is not going to be processed. But the only thing that comes after that is another null, so it's going to be null anyway. So it turns out you can do it this way. But this part of the code after this point is kind of a useless appendix. So it's not really going to have any effect. But it will work. You can do the same exploit in 64-bit compiled code and also get the UN message. And again, the crash. So that's good, clean fun. By the way, another thing you might do is wonder if this is going to work outside the debugger. The debugger's environment is not exactly equal to the real shellcode environment. Often things are off by 30, 40, or even 80 bytes. So let's test this exploit outside the debugger. If we quit, so if I run pwd 32 and take the input from that attack file, it does work outside the debugger. It gives me the uwin and then the segmentation fault. So this attack works fine outside the debugger. This is going to be a persistent headache as you go through this course. You'll develop an exploit that works in the debugger, and then when you try it outside the debugger, it will often fail. This is another reason to have a nice big NOP sled. If you have 100 or 200 bytes of NOP sled, it's more easy to point to the middle of the NOP sled, and then if moving it out of the debugger moves it by like 50 bytes, it'll still work. All right. So then there are a couple of challenges here. Like I said, this is the most important project in the class. This is where you learn all the essential features. This one will send a string to a remote server and run it through the same binary. And there are flags you can get. Because I learned how to program, I remember I actually did this on the airplane on the way to DEF CON China. I was on the airplane for like 14 hours with no internet, and I realized I could run a local virtual machine and I could develop remote exploits. So here you can send a string up to the processor. So let's try sending it AAAA and debug. And it's going to run GDB up on my server. So it shows you what it's doing. Here's my script. And notice my script now has some flags. And I've redacted the flag in the source code. The flag is not XXXX, it's something else. There's a couple of flags you can hit here. And notice right up here in the URL is the string you sent up, AAAA. So here it's going to disassemble and find the win function. And here it's going to do info registers, and here it's going to show you the stack. And there's the A's, AAAA. So I can eject something and see it here. So you have some goals to accomplish here. The first thing is send a string 31 characters long ending in ASCII code 7, a bell, to see the flag. So you just have to create ASCII code 7. Now let me point out something really important that a lot of students get confused about here. If I send AAAA here and debug, the way to do this is just work right here from the URL. Let me bring it up in a text editor. All right. So if you want to send a binary value up here, what you can do is modify that URL using the %sign. We're talking about this in the web exploit class. So if I wanted to send a binary 7, I would put %07 here. There's 3 of them, %07. This is how you send a raw hexadecimal value in a URL. So I sent 4 A's and then 3 7's. So let's resolve that one. right? And so if I go down here, here's my 4 A's. 1, 2, 3, 4 A's, and here's a 7. And here's 2 more 7s. That's how you send arbitrary numbers up in hexadecimal. So when you put a 7 in the right place, you'll get one of the flags. And the second one requires you, I think, to run the win function. So let me get back to my instructions. All right. And so then you have to run the win function, and you'll see the flag. And there's a couple of trips here. All right. And this is the URL encoding I just told you about. To send an unprintable character to the server, use % and then 2 hexadecimal digits to send encoding. Then you can exploit a 64-bit server.
Here's what I found.
And then this stupid, I still haven't found any way to make my stupid Apple Watch become insensitive to my voice. Anyway, this is, whenever you buy a new Apple device, you have to spend weeks trying to turn off all the garbage they have on it. Anyway, so here's various other exploits you can try here for lots of extra credit. And this is the real main point of the course, is learning how to do all these exploits here. So like I said, ED 202 is the heart of the course. And as usual, there's a little bit that I consider required and a whole lot of extra credit. So 40 points is the required stuff, and there's 75 points of extra credit. So get working on that and let me know how it goes. I'll stop this video.